Michael reaction. We have seen earlier that when nucleophiles react with alpha-beta unsaturated aldehyde or ketone, it can form either the direct addition product or the conjugate addition product. Here is the direct addition product, and this one right here is the conjugate addition product. In the direct addition, the nucleophile is going to get added to the carbonyl carbon, whereas in conjugate addition, it's going to get added to the beta carbon. This is the functional group, right? This carbon is alpha, this is beta. So the nucleophile is getting added to the beta carbon. Direct addition is favored by strong nucleophiles. So here we need to have strong nucleophiles, whereas conjugate addition is favored by poor nucleophiles. Now when the nucleophile that you use here for the reaction is an enolate ion, then it is called as Michael reaction. Here are two examples of Michael reaction. The first compound right here is an alpha-beta unsaturated aldehyde, and the one below is an alpha-beta unsaturated ketone. Now the enolate that works in Michael reaction is the one that is formed by using a dicarbonyl compound. So here is a dicarbonyl compound which has got two ester groups. So here are the two ester groups, and because of which these hydrogens right here is going to be very acidic. This compound can be conveniently called as beta diester because the two ester groups are in beta position with respect to each other. When you focus on this ester functional group, you can see that the second ester group is in beta position with respect to that, right? And this compound is a beta diketone because you do have two keto groups. Since enolates are weak bases, they are not going to do the direct addition with alpha-beta unsaturated aldehyde or ketone. Instead, they are going to do the conjugate addition. And in Michael reaction, a new carbon-carbon single bond is formed between an enolate ion that is obtained from the dicarbonyl compound and the alpha-beta unsaturated aldehyde or ketone. This is going to lead to the formation of 1,5-dicarbonyl compounds. Let's take a look into the product to see how this is going to be a 1,5-dicarbonyl compound and where is the new carbon-carbon single bond. The dicarbonyl compound is going to first form the enolate, for which one of these hydrogens will be abstracted, and with which this carbon will have a negative charge on it. So let's write down the enolate ion. So here is the enolate ion that will be obtained. And we said earlier that there will be a new bond that will be formed between the dicarbonyl compound and the alpha-beta unsaturated carbonyl compound. So if this is going to have a negative charge, there should be a positive charge on this compound, right? So this beta carbon will have a positive charge, right? This is an electrophilic site. And therefore, this will go and attack us as a nucleophile on this carbon, and it will form the new bond. And you can see that this part right here is carried from the enolate ion, right? And this one right here is the alpha beta unsaturated carbonyl compound, and here is the beta carbon. This is the beta carbon of the alpha beta unsaturated carbonyl compound, and this one right here is the alpha carbon of the dicarbonyl compound, and there is a new bond that is formed between these two atoms. Now let's see why this is called as a 1,5-dicarbonyl compound. If we consider this as the functional group, this is the first carbonyl group. The two carbonyl groups are separated by 3 carbons. So which means if you consider this as carbon number 1, and when you reach the second carbonyl group, this is in the 5th position, and therefore this is called as 1,5-dicarbonyl compound. And you can also go in the other direction, 1, 2, 3, 4, 5. The other carbonyl group is also in the 5th position with respect to the first carbonyl group. And therefore, this compound, the product that is obtained, is a 1,5-dicarbonyl compound. Let's see how a 1,5-dicarbonyl compound is obtained from an enolate ion and alpha beta unsaturated carbonyl compound. Here we have a beta diketone. So this one right here is a beta diketone, and here are alpha hydrogens. One of these alpha hydrogens will be abstracted by the base. So let's separate these two hydrogens here. So the base will come and abstract this hydrogen to form the enolate ion. That would be the first step. Now once the enolate ion is formed, the next is the addition reaction, conjugate addition reaction with the alpha beta unsaturated carbonyl compound. Let's draw an alpha beta unsaturated carbonyl compound. Here is our alpha beta unsaturated carbonyl compound, where these electrons from the enolate ion is going to make a nucleophilic attack on this electrophilic carbon. This is the beta carbon, right? And this one right here is the alpha carbon. And this is going to thrust in so as to push the electrons onto oxygen. Here is the intermediate that is obtained by adding the enolate ion to the alpha beta unsaturated carbonyl compound. Now you can see that this is our alpha carbon of the enolate, and this one right here is a beta carbon of the alpha beta unsaturated carbonyl compound. And there is a new bond that is formed between the alpha carbon of the enolate and the beta carbon of the alpha beta unsaturated carbonyl compound. Now in the next step, the alpha carbon will be protonated, for which these electrons right here need to come in to form a double bond between carbon and oxygen. And this will go and grab an hydrogen from the water molecule. And here is our final compound. And you can see that this is definitely a 1,5-dicarbonyl compound because they are, so the two carbonyl groups are separated by 3 carbons in between. So 1, 2, 3, 4, 5. So this would be a 1,5-dicarbonyl compound.